So it's a great pleasure to be here, and I'm looking forward to hearing all the exciting talks that are lined up for the week. Here's the Pan-STARRS logo and the title of the talk. What I thought I'd do is lay some of the basic foundations for the analysis that we do in cosmic shear and so on, give something of a preview of the stuff that we're going to hear a lot more about, the observational results, and then wind up to say a few things about future prospects, including our baby in Hawaii, Pan-STARRS. So we're gathered here, I think, primarily to celebrate this concordance model where the universe started off inflating, the seeds for structure were laid down, and is now inflating again, and we're trying to test that. So to put the cosmic shear into context, we've got basically these four fundamental tests of this kind of theory, of the growth of structure in this theory. The first is galaxy clustering, CMB, then bulk flows, something that's coming back into fashion now, and then weak lensing. So I thought I'd kind of contrast them. I mean, what we have in galaxy clustering is a way to measure, for instance, the power spectrum of the galaxy distribution. We've got low redshift surveys, pretty small volumes. Then we've got very large-scale two-dimensional surveys where you see the structure in projection. Of course, this was the stuff that Peebles and others developed, which was the first way we went about testing this kind of theory, and it seemed to work very well. But in a sense, the problem with this is the problem of bias, right? The different types of galaxies cluster differently. This is a sort of semi-analytic galaxy formation from the Munich group, I believe, and showing that, depending on what type of galaxies you select, will determine what answer you get from that. You can get around this to some extent by looking at the structure in redshift space. Here's the kind of analysis that people like Peacock and others have been doing, but it's still something of a problem. Then when you go to the CMB, you're looking at something completely different. Instead of looking at the local low redshift universe, you're looking at the universe as it was at high redshift. And we've got two sort of different types of phenomena that we're seeing here, which are actually nicely illustrated by the two most famous observational probes of this, which is the COBE, where you're looking at the large-scale stuff, and you're seeing the gravitational potential of the primordial ripples that later become the large-scale structure, and you're seeing the red shifting as the photons climb out of those potential wells. And that's very, very directly related to the present structure, because those potential ripples are, to first approximation, conserved in time as the universe evolves. And then you've got the second type of test, which is to use the higher angular resolution stuff in WMAP to test the geometric properties of the universe. So there's two things here. One is, what's the amplitude of the fluctuations? And then the other one is to ask about the global geometry of the universe. Right? So then bulk flows, somewhat similar to galaxy clustering, with the great advantage, though, that you're measuring the dark matter directly. You don't have to worry too much about the bias and so on. In fact, you can measure it directly. And again, you're relying on the fact that these potential, the way the structure evolves is that the potential ripples stay essentially fixed. So V delta V is constant. And that gives you growing structure and velocities that you can measure. And here's an example of a reconstruction of the velocity flows in the local universe. But that is the problem with this test, is that it's very hard to measure the expansion of the universe at all, right? It accurately. It's even harder to measure the deviations from universal expansion that you need to do to apply this test. And you can only do it very locally. And so you get enormous problems with cosmic variance. So that brings us to the statistical or cosmic shear weak lensing, where you can establish very similar relationships between the matter density fluctuations delta rho over rho and some observable. And it's, the steps are, you calculate the way that gravity deflects the light. You can't measure the light deflection itself, but you can measure the derivative of the light deflection, because that changes the shape of the background galaxies. And that's this shear thing, gamma. And you get this relationship. If you just had one structure in the universe, that's what it gives you. An observable, R's the size of the object, H is Hubble constant, D is the distance, and so on. And then we don't just have one structure in the universe, we've got large-scale structure throughout the universe. And so what you see is something which is the accumulated effect of random overdensities, underdensities, and so on. And it's nicely characterized in this picture that I stole from the LSST folks, though I've never understood this picture because it seems to be backwards to me, because the way I've always thought about lensing is I like to imagine an observer sort of looking out at a circular cone of rays from his or her eyes and asking what happens to those rays as they go back to the plane of the galaxies, and that circle will become an ellipse. And so you say, aha, if I had an elliptical galaxy there that just filled that ellipse, it would look circular, right, and vice versa. So anyway, I think this picture is nice because it sort of shows the shearing and the tidal effects, but it seems to be inverted to me, but maybe that's me. And as with the microwave background, one of the key things about this probe is that you have both geometric effects going on, that everything depends on these angular diameter distances. So that gives you elements of the observable that can tell you about the background cosmology. And then the other thing is it tells you about the amplitude of the structure, the potential fluctuations, and how they've grown, which is how we get at the dark energy. So here's a sort of rather a little bit more boring slide going over what I've just said. You calculate the deflection for a mass, that's what you get. And you could generalize that to get a two-dimensional Poisson's equation. You can't measure the deflection, but its gradient you can. And that's what we basically use. The next step in establishing the relationship from the observable, right, the surface brightness of things you look at as you see them is a mapping of the true surface brightness involving the second derivative of this potential. That potential is related to the dimensionless surface density. The dimensionless surface density is related to the physical surface density, and then via this inverse sigma crit thing. So that establishes how one can go from observables, how one can go from physical surface density to the prediction for what it does to the images. And the measurement technique, the first thing that was developed by Tony Tyson and Valdez and crew, was a really important step, was to realize that the way to measure this shear thing is to measure the moments, the x, y, y, and xy moments of the surface brightness of galaxies. So that gives you a little 2x2 symmetric matrix of which the non-trace parts are in fact the shear, and what they established was what we would now call the polarizability, which relates the observed polarization to the gravitational shear. Now this is a lot simpler than what people actually do, and we'll be hearing a number of talks about this, and here's a slide I stole from Gary that nicely illustrates what shapes map to in this ellipticity space. So let me mention a couple of other things. These were things which were noticed early on, and they seem to be somewhat not completely related to cosmic shear. One is if you had a map of the shear, how would you reconstruct what the surface density was that caused that? And one of the things that we realized is that if you measure the tangential component of the shear averaged around some arbitrary circular loop, then that turns out to be the derivative of the mean surface density inside that loop. So this is exactly like Gauss's law, where Gauss's law says if you integrate the normal component of the gravity over the surface of the Earth, you've weighed the Earth, right? And that's analogous